Hello guys, hope you are doing fine. So we were discussing like last video nearest neighbor search, and we discussed the regular indexing approach to find out the nearest points, data points, and when a point is given to us, and for that reason we actually follow regular indexing, which is 1D technique. 1D technique means what? 1D technique is like it is traversing the from this direction to that direction. So it is an one dimensional traversing, we can say, which a normal DB query executes, and it is going to take time because we are actually interested on this area, and this is an area, this is not a single dimension. So from here actually the inspiration comes, and the inspiration comes to govern a different technique. I think I am clear, right? Because if you just measure this area with one dimension, it is definitely going to take time. So is there anything which we can make an improvement here? Because we are actually running some queries, and these queries are normal queries, these range queries are normal DB queries. So that's why from this inspiration, actually instead of indexing on a single dimension, like previously we mentioned, like we have a table like id x and y, and on the x column we do indexing, on the y column we do indexing, and we are performing two range queries, so which is an expensive, and that was a big downside of this approach. We already mentioned that. So what is another approaches which we are talking about? So that is kind of a getting rid of 1D to some two dimensional. Yes, so there is something which is called spatial indexing, and that spatial indexing, if we talk like this, spatial indexing is actually a 2D stuff. It is considering 2D stuff. Probably it could sound a little different, but if we understood, if we go through this lecture properly and understood it clearly, trust me, it is going to be an easy concept for you. So it uses internally R3, and this R3 is actually very important data structure while we are doing something like while we are querying 2D stuff. So we will first understand like what is the thing, and we will understand it visually. Suppose this is our space where we have a lot of data points. We don't care about data points right now, we are having the space, and we are actually interested on to find a neighbor of, say for example, point A. And what we had done earlier also, we did like, with the help of a certain radius, we create a rectangle, right? So okay, the basic assumption here, we will be including rectangle only, no other kind of geometric figure, right? So we are creating this rectangle, and we are trying to understand like what is going to be the nearest neighbors of point A. So we took a projection on x-axis. So this is our x-axis as we mentioned earlier, and this is our y-axis we mentioned earlier. That is perfectly fine. Now in x-axis, on the x-axis, we got a projection like x1, we got a projection like x2. Fine. Here also in case of y-axis, we got a projection like y1, we got a projection like y2. Fine. And that is actually going to the axis which is parallel to y-axis, that is going to axis which is parallel to. Fantastic. Now here actually that was the thing which we did earlier, and we started querying one in one direction. Now let's forget that approach. Let's forget that approach and try to understand that you have total 9 boxes, and you are interested on this box. So you are actually trying to find out an algorithm which will give you the result or the data points which lies in this box only. How are you gonna do it? So out of 9 boxes, you are interested on a box which encloses your desired points A, your design point A. And to do that, we need to go to the basics of R3, and the query, it is doing? So first of all, step one, let's take another example. Suppose you got some point, heartbeat point. Suppose you have some points like this, right? You have some points like this, and you got some points like this, heartbeat point. So first you have to, suppose these are 3 points you have altogether, okay? And you have to find out a, or you have to find out a triangle which encloses, means which is kind of a bounding box of these 3 points. Bounding box means what? Means the boundary of the box will have these points, okay? And you will set it in such a way so that one point becomes the left corner or resides very close to left corner. So if we draw, if we try to drawing a triangle with the, with the, sorry, a square with the help of these 3 points, data points, whereas we want to keep in mind that box is going to be a bounding box, and the, you know, the data point is going to be as left as corner as possible, then you can take, you know, you can take an edge on this, right? So you just can do like this, okay? See, you can do like this, right? You can do like this. You got a corner point over here, you got a point like it is also, you know, lying to the corner, right? And there is another point which is lying on this box. Fine, fantastic. So just name these points. One, suppose this is your 2 and this is your 3, and the name of the box is A, for an example. Okay, now what you are doing, you got some other points, okay? Suppose this, you got this, and you got this. So what you trying to do, you will, you know, try to draw your rectangle over here and just name these points. Suppose you got 4, you got 5, you got 6, and the box name is P. Fantastic. You got other 3 points, okay? The same thing you are going to do over here as well. Suppose you got these 3 points, so from this corner you try to draw it. Yeah, that is fine, and yes, that's perfect. So you have drawn box number C. You have, this is for example 7, this is 8, this is 9. Now what they're suggesting, whenever you are having completed with this step, like you got some points, data points, you have drawn some, you know, squares, rectangles, which follows those two principles. Like first of all, it should be like bounding boxes, and second of all, you have to align these points in such a way so that it becomes very close to the corner. And why corner? Because you want to align x and y axis, nothing else. And now you have to set a triangle on top of this triangle. So how you gonna do that? So first of all, you have to, suppose this is your triangle, I'm just making a dot. This is very close, just embracing this, you know, 3 triangles, okay? Okay, that's perfect, that's perfect. So you are just, okay, this is your point 1, okay? And you are naming this, you have box, sorry, you have box A, you have box B, you have box C. So you're naming the outer box, say for example D. So how many boxes you have right now? You have 4 boxes, D, A, B, C. Fantastic. Now think that every box actually is having the feature like it's a bounding box, right? Second thing, every box has 3 elements. How? If you consider box number A, box A, it got 1, 2, 3, 3 points. I'm saying elements. So A box, if you just say A box has got 3 points as elements, all right? Similarly, D box is having 3 boxes as elements. That is fine, that is fine. But the thing is, here what you are trying to do here with this picture, with this analogy, you are trying to draw some bounding boxes which got 3 stuffs with got three elements, whether it's a point, whether it got boxes. The abstraction layer of the whole boxes, which is box number D, is also having three boxes. So that means you are aligned with the expectation of this algorithm, right? Which is kind of coming from in the arrangement phase. So if you want to write or draw a tree with the help of this, would you like to, can we say like D is the root tree, root node of a tree, and D is having actually three nodes altogether, A, okay, B, okay, and C. And A is having 1 2 3, right? 1 2 3. B is having 4 5 6, and C is having child like 7 8 9. Understand it clearly. So that means you are maintaining the property like everyone has got three elements for this example only. Now you can say like what this R tree suggests us when we are doing this type of query, or when we are handling this type of query. This suggests you can go up to 9. Why I am coming into the point, I will be discussing that one. But first understand that whether we are able to map with a tree or not. We are able to do that. That's perfectly fine. This is an R tree which is having 3 children. Good. Now suppose we are given two methods, two functions. One function is overlap, another function is which takes two arguments, rectangular 1 and rectangular 2. Another function which talks whether rectangular 1 is having a point or not. Okay, these two functions you are given, and you are given through some pointers or through something which actually traverse your tree. Now what that something will be? Actually you have a tree of rectangles. Now your pointer also has to be a rectangle, right? So suppose you got a pointer kind of thing which is say it is X, and it's kind of a thing like this, the dotted one, X. So you're just traversing those pointers, you are just traversing that pointers, and whenever you are traversing, you are saying like, is there any overlap between R1 and A and B? You don't have any overlap. Why it is not having overlap in this picture? Because the three boxes locations perspective, they are parts, they are very differently located. So you can increase the size of your boxes because there are no neighbors is finding, so you can increase the radius, and you can whenever you are increasing your radius, you will be having kind of a big box, and you are trying to find out neighbor as because neighbors are not very near here. So if you just enhance your size of X box, probably you got an intersection between A and between box P, and that is saying like you got two people within that box, and mean you got some overlapping, and that is 3 and 4. That exactly our answer is. That is exactly what we are looking for. Now the thing is, if we want to add some point or let's start from the let's see how we find any point within this box. So we have to start from the root if we want to traverse it. Root doesn't have any point, okay, and go through the roots to the children, and we see that children is having some overlapping or not, right? That is the thing what exactly we are trying to do, and that is the thing what exactly we are trying to show with X, right? Now the size of query box, you can say like X is actually our query box, you can say like that. Now the size of query box, as I was discussing, is pretty small. So only have to traverse through few triangles, and that is going to be fine. Usually you, I mean, pretty small with respect to this box, I mean the given box. Okay, so you don't have to traverse every triangles, right? So now the question is usually if you see, like, you have to limit the result when you are if whatever the result is coming, you can limit the result. Say for example, I want first 2000 result or first 3000, something like that to make your program much faster and efficient. Now, another important note I would like to say, which actually I was trying to discuss from this figure, that if your tree is having great height, then your program might take time or will take time rather. But here, if you have, almost 10 to the power 6 data points, right, and your tree having 3 children, so what is going to be the height of the tree? Log 3 base 10 to the log 10 to the power 6 base 3, and this results almost 13. Now if you got something like log base 9 into 10 to the power 6, that is going to result probably 7, I guess, which is a very very efficient. So that means you don't need to bother about the height of the, which is good thing, good sign, like your program is not taking much time, right? Now the question is, if anything comes, for an example, you are trying to do some insertion. Now any points coming here, uh, that is point number 10. So how will you incorporate it? Try to understand it. How will you incorporate it? You already having 3 stuffs within this rectangle, you want to add something. So max, you can keep 3 children, right? So you just can split these things. I mean, you can write, this is my A, I'm drawing faster, this is my B, okay, this is my B. It don't change because it already got 1 2 3 and 4 5 6. Only the change is going to happen with, so 7, suppose you are having 7 and you are having 9, so you are having 9 over here, you are having 7 over here, and the thing is, this is your modified C, and you got something called D. So D is very much aligned to 8. So suppose you got something like this, so you got 10 over here, you got 8 over here, for an example. Now there are 4 entities, right? So A, B, C, D, and we said like we are not keeping more than 3. So either we can go with, like, we can go with A, B children, right? A, B, a box, we can top up that. There is another box which is A, B, C, D. So you can say like this is E, this is F, I'm sorry, yeah, and we can say like there is another box on top of this, this is G. So our modified tree would be like G is going to be a parent node, then we will be having E, then we'll be having F, right? E and F are in the same layer, and E is having A and B. A and B is non-impacted, so it will got 1 2 3. B is going to have 4 5 6. In case of F, we are having 2 boxes, so C and D, and C is having only 7 and 9, so this is 7, this is 9, and D is having 8 and 10, right? So this is the new tree after the insertion. So we need to think about this thing. And one more important thing, it is happening on memory. So this R tree is performing on memory, so it's going to be quick. So you can, the whatever the query we are talking about for a long time, that we want to run a 2D query on R tree with a special indexing, and these are the range queries, which is going to be faster because we are making a rectangle as our query box. So thanks for watching. Hope this video is an effective one. So please put your comments into the comment section. Thanks a lot.